Hello guys, you're welcome. In today's video, we'll be looking at Introduction to Organic Chemistry. Please, after this video, feel free to subscribe, feel free to like, feel free to share as well, and of course, comment if you have any question whatsoever. All right, so like we have on the board Introduction to Organic Chemistry. It's important to understand that organic chemistry is a very key aspect of chemistry that cannot be ignored. So what then is organic chemistry? Organic chemistry is the study of organic compounds. And organic compounds are compounds or substances obtained from plants and animals. So any substance that is gotten from plants, that is gotten from animals, is known as an organic compound. Now, at this point, it's important for us to know the history of organic chemistry. How did organic chemistry come to life? Now, it's important to understand that there were scientists who individually made it their duty to discover compounds, to discover substances, which led to the birth of organic compounds and, of course, by extension, organic chemistry. Now, in the late 1700s, 1770s, and 1780s, precisely, a Swedish scientist known as Carl Wilhelm, like I said, in the 1770s and 1780s, respectively, isolated two compounds which happened to be organic compounds. Isolated, the first one was citric acid in the 1770s and lactic acid in the 1780s. All right, so he isolated citric acid from lemon and isolated lactic acid from milk. As you know, lemon is a fruit, of course, a plant. Milk is gotten from animals. All right. So it's important for us to understand that this scientist was actually one of the oldest scientists that led to the discovery of organic compounds. Many years later, of course, in the year 1828, another scientist, a German scientist precisely, known as Frederick Frederick Wohler. I will spell it so Frederick Wohler. Frederick Wohler discovered urea, and urea is a component of urine. It's a component of urine. How did he discover that? He discovered urea by heating an inorganic compound called ammonium cyanide. He applied excess heat to ammonium cyanide, which led to the production of urea. And of course, this was done in the chemical laboratory. All right. So ammonium cyanide has a structure, and the structure of ammonium cyanide is like this. We have NH4 plus NCO minus. All right. This is ammonium cyanide. So he applied heat, which led to the formation of urea. And urea is like this. This is the structure of urea. All right. So this is the structure of urea. So this is ammonium cyanide, and this is urea. All right. So he applied heat to this, which led to the formation of this. And urea happens to be an organic compound as well because it can be gotten from animals. All right. So it's very important for us to also understand that these scientists had specific functions that of course led to the formation and discovery of these compounds. What then are the functions of these scientists that we of course we can call organic scientists? In organic chemistry, anybody that is studying organic chemistry is an organic chemist. All right, like you, like me. All right, we are studying organic chemistry. So yes, we're organic chemists. What is actually the role of an organic chemist in the development of organic chemistry? Number one is called structural elucidation. Structural elucidation happens to be the explanation or the illustration of the structure of organic compounds. So it is your duty, it is my duty to look at the structure and explain the structure of an organic compound and explain the structure. By virtue of this series, we'll come to understand the structures of organic compounds and their nomenclature, how to name them as well. These are very key aspects that we cannot ignore. Number two is what we call the synthesis of compounds. How are these compounds formed? Synthesis is more like formation, it's more like production, it's more like development of these organic compounds. So that's number two. We look at how these organic compounds are produced and formed and synthesized. Number three is what we call the study of the reaction mechanisms of organic compounds. How do organic compounds react to form products? Very important. How do inorganic compounds as well react to form organic compound? Just like ammonium cyanide, which happens to be an inorganic compound, which was actually transformed to urea through the application of heat. Transformed to urea through the application of heat. So these three things are very, very important. Now, along the line, organic chemists proceeded in discovering more organic compounds. But there was something that they discovered that made them to develop a theory called the vital force theory. What did they discover? They discovered that most of the organic compounds that they were actually synthesizing were having some elements common in them. And the common elements in organic compounds are carbon, nitrogen, oxygen, and of course hydrogen. Okay? Organic compounds that are commonly used in today's world are called hydrocarbons. And hydrocarbons are organic compounds that are composed of carbon and hydrogen. Carbon and hydrogen. These four elements, carbon, nitrogen, oxygen, and hydrogen, are the most common elements in organic compounds. It's very important to note that. Now, I want us to also understand another concept that we'll be looking into, and this concept is known as empirical and molecular formula of organic compounds. So we'll be looking at the empirical and the molecular formula of organic compounds. Now, it's very important to understand that we cannot actually recognize and identify an organic compound if we don't know the molecular formula of that organic compound. We know inorganic compounds like, of course, hydrochloric acid, HCl. We know tetraoxosulfate 6 acid, H2SO4. We know HNO3. We know bases like NaOH, KOH. We know salts like NaCl. We know KCl and on. Now, these are inorganic compounds. And it's very easy for us to identify these inorganic compounds because of their formulas. And it's their formulas that contains the elements. And it's because of these elements that we can be able to identify these compounds. So how do we come to a good understanding of organic compounds through empirical and molecular formula? Now, the first thing we must know is that the empirical formula of a compound is the formula which consists of the simplest mole ratio of the constituent elements in that compound. It shows the smallest number of constituents that can exist in a compound. And on the other hand, the molecular formula shows the actual number of moles of the constituent elements in an organic compound. Just like in this context, we are looking at organic compounds. That's why I'm using organic compounds. All right. So this one is the simplest mole ratio, while this is the exact number of moles of the constituent elements in an organic compound. All right. Okay, as I earlier said, empirical molecular formula are very crucial in identifying organic compounds, and it's very important to understand that it is also a huge parameter or factor in the basic analysis of organic compounds. Now, let us look at the question that will help us to appreciate empirical molecular formula the more. Now, look at this. 0.404 grams of an organic compound A gave on combustion gave on combustion 0.722 grams CO2 and 0.294 grams H2O. Full stop. Now, if the relative molecular mass of the organic compound relating molecular mass of the organic compound is 150, find the empirical and molecular formula of the compound. I want you to take your time to write down this question, take down this question, okay, and we would actually solve it. Very important. Okay, so 0.404 grams of an organic compound, a given combustion. If you look at it, you realize that there is a word here, combustion. What is combustion? So combustion reaction is actually a reaction in which an organic compound burns completely in the presence of oxygen gas to liberate carbon dioxide and water. So whenever an organic compound burns in the presence of oxygen gas O2 and carbon dioxide and water are formed, that reaction is known as a combustion reaction. So it's a very crucial reaction in organic chemistry. Yes, very crucial. There are many things that evolves as a result of it. We'll look at it by virtue of the reaction mechanisms and types of reactions of organic compounds. All right, so let's solve this first. All right, let's solve this first. Now, if you look at this particular question, you realize that unlike normal empirical and molecular formula questions, you'll be given either the mass of the elements or their percentage composition. But here, you're not giving the mass of the elements, rather, you're giving mass of compounds. Now, look at it very well. You will now see something here. All right, you realize that the elements that are here are carbon, oxygen, and hydrogen. Carbon, oxygen, and hydrogen. How do we now get the mass of carbon, the mass of oxygen, the mass of hydrogen from these compounds? How do we do that? All right, so that's what we would actually do now. Okay, that's what we'll actually do now. So at this point, I believe you've taken down the question, so I'll be cleaning the question. All right, so we can solve. Cleaning the question so we can solve. All right, so now it's important that while we are solving any question, we must first of all list the parameters. Now we have mass of A. Mass of A is 0.404 grams. CO2 is 0.722 grams, while H2O is 0.294 grams. Now, as a matter of fact, these are the masses that are in this question. Then, of course, we shouldn't forget that the relative molecular mass is 150. Of course, we will not be using that for now. Okay, but now let us first of all get the mass of carbon, oxygen, and hydrogen first. All right, now if you look at it very well, you realize that carbon is in carbon dioxide, hydrogen is in water, while oxygen is in both of them. It's important to note that this 0.404 grams you're seeing here is composed of the mass of carbon plus the mass of hydrogen plus the mass of oxygen. So it means that this particular compound has carbon, hydrogen, and oxygen, CHO. Now it's our duty to actually know the mass of these particular elements, each of them in the compound, and use it in solving the empirical formula and also the molecular formula. So now let us look at it. So now in order for us to get the mass of an element, so now let's look at this formula. Mass of element in compound. Please take note of this formula, don't forget it, to help you. Mass of element in compound is equal to mass, molar mass rather, molar mass of elements in compound, molar mass of elements in compound divided by molar mass of compound times mass of compound. So we have to divide the molar mass of the element in the compound by the molar mass of the actual compound times the mass of the compound. That's how we can be able to get the mass of the element in compound. How do we do that? Now let us solve that. I believe we've written this. So now let's go down here and solve it. Now the molar mass, let's start with mass of carbon in CO2. All right. So we have to first of all look for the molar mass of carbon. Molar mass of carbon is 12. We don't need to break our heads for that. It's 12. But in CO2, carbon is just 1. What we mean by molar mass of element in compound is that for us to get the molar mass of the element in compound, we need to take note of how many atoms of that element is in the compound. They will multiply the normal molar mass by the number of times that particular element appeared in the compound. Look at what I mean. Carbon is 1 here. Molar mass of carbon is 12. But if carbon were to be 2 here, we'll say 12 times 2. That will give us 24. But we are going to use only 12. We are going to use only 12 here. And we'll divide it. We'll say 12 divided by, so the molar mass of CO2 is 12 plus oxygen is 16. 16 times 2 is 32. So 12 plus 32 is 44. So we say 12 divided by 44, then multiplied by the mass of the compound. Mass of the compound, mass of CO2 we are using from the question is 0.722 grams. Okay, let me get my calculator. All right. So I hope you have yours as well. Now, so we have 12 divided by 44, then multiplied by 0.7722. All right. 0.722. So the answer here is 0.1969 grams. All right. So it's important for you to be very careful of approximation. 3 or 4 decimal places is okay. It shouldn't be anything less. Don't use 2 decimal places, except that is exactly what your calculator gives you. All right. So 0.1969. Okay. So now let us look for that of hydrogen. So hydrogen is in water. So we say mass mass of hydrogen in H2O in water. So hydrogen in water is 2 atoms. Normally, the molar mass of hydrogen is 1. So 1 times 2 is 2. So we say 2 divided by 2 plus 16, 18. Oxygen is 16. So well, this is the molar mass of the compound. Then times the mass of the compound that was given to us in the question is 0.294 grams. Hope you haven't forgotten. All right. So we say 2 divided by 18, then times 0.294. Okay, so what we have here is equal to 0.0327. Okay, 0.0327 grams, all right, of hydrogen. This one is of carbon. All right, so 0.0327. Now the next thing we have to do is to get for oxygen. All right, how do we now get for oxygen? Now, how do we get for oxygen? To get for oxygen, we need to understand that we don't need to go through the stress of looking for oxygen in carbon dioxide and looking for oxygen in water. No, let's not do it like that. Now, the organic compound has a mass of 0.404 grams. So it means that this 0.404 grams, like I said, has mass of carbon, mass of hydrogen, and mass of oxygen in it. It's just like having the sum of the ages of 3 children. They say the ages of 3 children, Kego, Emeka, and Chukwuebuka, okay, are 40 years. And Kego is 16 years. Chukwuebuka is 14 years. All right, Chukwuebuka is 14 years. So it means that the third child would be the general age minus the age of the Nwakigo and Chukwuebuka that you already know. That's how you will get the age of the third child. So you don't even need to ask of the age of the third child, provided that you have already been told that when you add their ages, that is 3 of their ages, you will get 40. And you already know the age of 2. So what you just have to do, add the age of the 2 and subtract it from the 40 that you already know. That's how we'll have to apply it here as well. So the mass of the compound is 0.404. So we'll say now minus, all right, we already know 0.1969 to be the mass of carbon, and then we know the mass of hydrogen to be 0.0327. All right, so now what we have to do is that we'll add these two, then we'll subtract it from this. All right, so we'll say 0.1969 plus 0.0327. So this is, so we say 0.404 minus 0.2296 after adding these two. All right. So let us subtract. So 0.404 minus 0.2296. So this will give us 0. So this will be equal to 0.1744 grams of oxygen. So now at this point, we have been able to know the mass of oxygen to be 0.1744. So it means that this plus this will give us 0.404, which is the total mass of the organic compound A. All right, so now let's look at this. We are still proceeding. All right, we are still proceeding. Now we can wipe this so we can go straight into solving the actual question. All right, to get as you can see, we have gotten the mass of carbon, hydrogen, and oxygen. Now we have to go straight to solving the empirical formula and also the molecular formula. So let's solve the empirical formula first. So I'll be creating a table, all right, a table that will help us to get the empirical formula. All right, so this table will be drawn like this. So we'll have carbon here, we'll have hydrogen here, and we have oxygen here. Now, this area is for the factors to consider. When solving for empirical formula, the first thing you must do is to calculate the number of moles. All right, number of moles is mass over molar mass. Mass over molar mass. Now the mass of carbon here is 0.1969. Molar mass of carbon is 12. So if we divide 0.1969 by 12, that will give us 0.0164. So 0.0164. All right, so mole. All right. Now for hydrogen 0.0327 divided by molar mass of hydrogen is 1. So of course 0.0327 divided by 1 will still give us 0.0327 mole. You have to be very careful with your values. Then for oxygen gave us a mass of 0.1744. When we divide it by the molar mass of oxygen, which is 16, so we have 0.1744 divided by 16. This will give us 0.0109 mole. Now, the next thing is to divide everything by the smallest mole. If you look at all these values, realize that the smallest mole here is 0.0109. All right, it is smaller than this and this, so we have to divide it by 0.0109. So we divide by smallest mole. So dividing by smallest mole give us the mole ratio. All right, so if we divide 0.0164 by 0.0109, let's do that together. All right, this is the technique you must always apply. All right, 0.0164 divided by 0.0109. All right, so 0.0109. Okay, so we have 1.5. All right, then we have 0.0327 divided by 0.0109. So this will give us, so if we do 0.0327 divided by 0.0109, this will give us 3. Now 0.0109 divided by itself, 0.0109, this will give us 1. Now, if you look at this, you realize that we are having decimals, but we are not supposed to be having decimals as our mole ratio. Okay, mole ratio are supposed to be whole number. Remember, empirical formula are formulas that consist of simple whole number ratios. It has the simplest whole number ratio. So 1.5 is not a whole number. All right, so whenever we have decimals like this, the next whole number that we have to multiply, the next value we have to multiply or factor, we have to multiply to get a whole number is 2. Because if we multiply 1.5 by 1, it's still going to be 1.5. 3 times 1 is still going to be 3. 1 times 1 is still going to be 1. So we have to now multiply. When you have a case like this, even if it is just one number, okay, one number, one value that is decimal, ensure you multiply everything by 2. The aim of multiplying everything by 2 is so you can be able to get a whole number. So if we multiply 1.5 by 2, we are going to get 3. Okay, so now we say multiply by 2. So 1.5 times 2 will give us 3. 3 times 2 will give us 6. 1 times 2 will give us 2. All right. So when we multiply each of these values, okay, we'll have 3, 6, and 2. So what it clearly means now is that our simple whole number ratios are 3, 6, and 2. All right. So that brings us to our empirical formula. So it means our empirical formula EF will be C3 H6 then O2. So this is our empirical formula. Okay, I believe it's clear. I believe you understand. Now, the next thing is to calculate a molecular formula. All right, so having understood this, let us calculate a molecular formula. Now, our molecular formula, okay, a molecular formula can be gotten by actually determining, okay, the ratio of the relative molecular mass and the formula mass. Let me just give you the formula. All right, molecular formula is equal to empirical formula N. This N is relative molecular mass divided by the formula mass. All right. Relative molecular mass that was given to us in the question was 150. So remember, relative molecular mass was 150. Don't forget that. It can be different based on the question, but in this particular question, relative molecular mass is 150. Now, the next thing is to know what formula mass is. Formula mass is like the molar mass of your empirical formula. Let us get the molar mass of the empirical formula. So we already know that relative molecular mass is 150. Formula mass now is the molar mass of your empirical formula. So let's get the molar mass of the empirical formula. Carbon is 12, okay? The empirical formula is C3H6O2, right? So carbon is 12. 12 times 3, all right? So 12 times 3 will give us 36. 36 plus hydrogen is 6, right? 1 times 6 is 6, so 36 plus 6, then plus oxygen is 16. 16 times 2 is 32 plus 32. So this will give us 74. All right. So this is 150 divided by 74. So this 74 is the molar mass of C3H6O2. All right. So it means that 150 divided by 74 will give us 2.02. So this is 2.02, which is of course 2, approximately 2. Okay, this is approximately 2. So it means that now please note that your n must be a whole number. Please round it up to the nearest whole number. All right, round it up to the nearest whole number. And please let me explain something. Let me explain that 1.5 that we got. Please, the reason why we multiplied it by 2 is because you cannot approximate 1.5 to 2, and you cannot approximate 1.5 to 1 when it is zero point 0.5. When it is approximately zero point 0.5, ensure you multiply by 2. Even if it is only one value there that is 0.5, ensure you multiply by 2. I had to bring this up again because I don't think I really expatiated on it that time. All right, so please note, if it is 1.4, okay, then you can round it up to 1. If it is 1.7, you can round it up to 2. But 1.5 cannot be rounded up to 1. It cannot be rounded up to 2. So you must multiply it by 2. And multiplying means that it will affect everything, not just that one. All right. So, but for this case, okay, for this particular case, you would always get a value that you can either round up to 2 or round up to 3. For your n, it is almost impossible to have zero point 0.5 as your n. All right. So any value you get, most times it's just the whole number itself. All right. You will not need to round up, but in this case, 2.02 is still 2. It's still 2. It's okay. So 150 divided by 74 is of course 2. So it means that our molecular formula, our empirical formula is C3H6O2. So N is what? 2. So this 2 means that it will multiply inside. So it means that it will be C, 3 times 2 is 6. 6 times 2 is 12. Then for O, 2 times 2 is 4. So this is the molecular formula. All right, this is the molecular formula. Okay, so this is just one form of analysis. I'll give you more exercises on empirical and molecular formula that will help you to appreciate this better. Now we'll be looking at another thing. I believe you've written this down. You can pause it and write it. We're looking at another concept of analysis of organic compounds, and that is called index of hydrogen deficiency. Okay, guys. Now we'll be looking at index of hydrogen deficiency. From the word index, you'll come to realize that it has to do with numbers. Hydrogen deficiency has to do with lack. You know, deficiency means lack of hydrogens. Now, it's important and sacrosanct to actually understand that in an organic compound, there is a required number of hydrogen atoms that is meant to be present. If hydrogens are deficient, it means that that particular organic compound is not accurate. The formula is incorrect. So it's important, it's sacrosanct to understand that if we are calculating the index of hydrogen deficiency and your IHD, for instance, is giving you 1, it means that that particular organic compound is lacking 1 hydrogen. If it's giving you 2, that organic compound is lacking 2 hydrogens. If it's giving you 0, it means that that organic compound is accurate, the formula is accurate, it's not lacking at all. But if you're having a negative value, for instance, -1 means that it's having excess of 1, -2, excess of 2, -3, excess of 3. So IHD is a very important tool in properly analyzing the accuracy of the numerical strength of hydrogen atoms in an organic compound. So let's delve into it. Let's delve quickly into it. All right. So I'll be giving you the shortcut on how to calculate IHD to avoid too much grammar. All right. I'll be giving you the shortcut. So the formula for IHD that is actually shorter, all right, that will help you to determine the index of hydrogen deficiency is equals to 2C minus H minus HAL plus N plus 2 divided by 2. Now C is number of carbons, H is number of hydrogens, HAL is number of halogens. You know, halogens are group 7 elements like chlorine, bromine, iodine, fluorine. Okay, we also have this chlorine, bromine, iodine, fluorine. All right, these are the major ones. All right, these are the major ones. So then that's halogen. Then N is number of nitrogens, or basically group 5 elements in group 5. All right, elements in group 5. So these are very important things we must take note of, okay, when we are using this formula. All right, so oxygen is also not inclusive in calculating IHD. Even if the molecular formula contains oxygen, it's not inclusive. These elements are the only ones that are necessary. If it's not a halogen, if it's not a group 5 element, if it's not hydrogen, if it's not carbon, please forget about it. Even if oxygen was part of the vital force theory, but here, oxygen is not a factor to be considered. Why? Because oxygen forms double bonds. I will explain more of this in hybridization. All right, I will explain more of this in hybridization. So take down this, you can pause it and take down the formula. This is 2C minus H minus HAL plus N plus 2 divided by 2. Now let's look at one example. All right, let's look at one example. Okay, so now please take down. So let's determine the IHD, index of hydrogen deficiency, of the following. So number one, let's say C3H8O. Number two, let's say C5H12NO2. Number three, let's say C2H5Cl2. All right. Then let's say C5H12F. Okay. All right. So let's work with these four. Let's work with these four to calculate the IHD. Now let us first of all, let's start with C3H8O. Let's start with C3H8O. All right. So C3H8O. So remember, the formula is 2C minus H minus HAL plus N plus 2, all divided by 2. Now 2C will be 2 times 3 minus H. Hydrogen here is 8 minus HAL. There is no halogen here, so we skip that. We skip that. There's no nitrogen here, we skip that. So we'll go to plus 2, all divided by 2. This is the plus sign. Okay, so 2 times 3 is 6. 6 minus 8 is minus 2. Minus 2 plus 2 is 0. So we have 0 over 2. So 0 over 2 is what? 0. So it means that the 8 hydrogens that are here is the actual number of hydrogens that are supposed to be here. It means that this molecular formula is correct. Hydrogens are not lacking, hydrogens are not excess. So there is no deficiency of hydrogen here. So we're having 0. All right. Hope you understand. All right. So now let's look at the second one. C5H12NO2. C5H12NO2. So C5H12NO2. So we'll have 2 times 5. We are still using this formula. Minus hydrogen is here at 12. There is no halogen here, so we don't need to put minus halogen. There is nitrogen here, 1 nitrogen. So we have plus 1. Then we remember we ignore oxygen. Let's just go to the plus 2. This plus 2 is like a constant value there, divided by 2. All right, so 2 times 5 minus 12 plus 1 plus 2. So this will give us 2 times 5 is 10. 10 minus 12 is minus 2. Minus 2 plus 1 is minus 1. Minus 1 plus 2 is 1. So we have 1 over 2. So when you have a fraction like this, there's nothing like half hydrogen. Okay, so you just say 0.5. All right, 0.5. There's nothing like half hydrogen. This particular compound almost does not even exist. The fact that you're even having a decimal value. Let's check it again. 10 minus 12 is minus 2. 10 minus 12 is minus 2. Minus 2 plus 1 is minus 2 plus 1 is minus 1. Minus 1 plus 2 is 1. So it's 1 over 2. We are correct. All right. So now let's look at the next one. C2H5Cl2. 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 All right. So this will be 2 times 2 minus 5, then minus 2 plus 2. This minus 2 is coming from the chlorine here, all divided by 2. All right, minus 2 plus 2 is already 0. So 2 times 2 is 4. 4 minus 5 is minus 1. So we are having here, so the answer is so the answer there will be minus 1 over 2. Minus 1 over 2. All right, which is minus 0.5. Okay, then next one, C5H12F. Please try that one. So you try the last one that I gave. All right, so this is general idea. You multiply 2 by the number of carbons, subtract by number of hydrogens, minus 2. From the formula, there is no nitrogen. That's why I just did minus 2. Then I went to plus 2. 2 times 2, 4. 4 minus 5 minus 1. Minus 1 minus 2 is minus 3. Minus 3 plus 2 is minus 1. That is minus 1 over 2. So that's the general idea of um, index of hydrogen deficiency. All right, I'll give you more exercises that will help you appreciate IHD the more. So it's very important in analyzing hydrogen atoms present in an organic compound. Please do well to subscribe, share this video. You can also comment if there's any way you are actually confused, you have a question, please do well to ask, and of course like this video and look forward to next videos, all right, on this series of organic chemistry. Thank you and goodbye.